I'm Asian myself. Caucasian. Okay, so we left off yesterday talking about the periodic trends, and we remind ourselves that periodic trends are functions of the most important principle in all of physical science, and that is opposites do what? Attract. While likes do what? Repel. So electrons and electrons repel, but electrons and protons attract. And ultimately, if you're an atom, your ultimate goal is to get an octet. So you want how many valence electrons?
8.
8. That's an octet. So electronegativity, this is a different diagram that I had up yesterday. Electronegativity is the idea that elements that are close to having an octet are going to work really hard to get that last electron. Okay? So look at fluorine and chlorine and bromine, they almost have their octet, so they're going to work really hard to complete their octet. Similarly, oxygen only needs 2 more electrons to complete its octet. It's going to work really hard too. On the other hand, when you have elements on the other side of the periodic table, look at your, what we're going to be calling the alkali metals. These have a very low electronegativity because they've got 1 outer electron. They're not interested in getting more. They have very low electronegativity. And we're going to use this principle a lot when we talk about bonding. Yeah.
Wouldn't they want to get rid of that one instead?
But it's still, well, it's still valuable to them. All electrons are valuable. So while they're not going to hold it very securely, they're not just going to be like, get out of here, we don't want you here. They still want it, just not very well. Okay. It's kind of like pennies. You know, if you're walking along and you drop a penny, you're like, you know. But still, you're not going to like, just, you know, like pennies and throw your pennies away.
Oh, yeah.
You're going to keep them in your pocket, but if you drop one, you're probably not going to reach down and pick it up.
Too much work.
Yeah. That's what all the surveys said. They said like 60% of Americans would not reach down and pick up a penny if they saw it on the ground. Only if it's shiny. It's shiny. Okay. So and then we talked about ionic radii, and we remember that we have anions, which are negatively charged ions, and they are always larger than their neutral atom, and cations, which are smaller than their neutral atom, because, well, why? Why do we have this? Why does this happen? Why are anions always larger than their neutral atom? You add something. You add an electron, and what does that do to the atom?
Oh yeah, the it has something to do with the orbital. No, maybe. I remember it. Brain not working.
Okay. Anyone else want to develop that? It does have something to do with the electrons. What do electrons do around other electrons? Repel. Yeah, they repel. Carson.
Well, when you put an extra electron, they have to spread out because light repels.
Exactly. So the more electrons we have, the more repulsion there is. So by adding an electron boop, to the cloud repels and the cloud gets bigger. Similar happens when you take away an electron. Boop. Take away an electron, there's less repulsion and that cloud gets smaller. In fact, sometimes we take away that electron, boop, the whole atom shrinks down to its inner shells. So sometimes that whole shell gets shaved off. In the case of sodium, that's exactly what happens. With sodium, you lose 1 electron, and the whole third shell gets shaved off. Bye-bye third shell. Okay. Does this idea make sense? This is where we left off last time.
Yeah.
Give me a thumbs up if we're good. Okay, cool. So now we're going to talk about specific groups and their properties. But before we talk about specific groups and their properties, we must talk about something called oxidation. So we remind ourselves that elements in the same group have similar properties as periodic law. Oxidation is both the difference between the protons and electrons of an ion and the charge an atom has when it completes its octet. So oxidation is the charge something has when it completes its octet, when it bonds. And oxidation is going to be a huge deal in the next few units. So let's follow the little green dot to the periodic table and remind ourselves about valence electrons. So here we find group 1. How many valence electrons does group 1 have? 1. 1 valence electron. How many does group 2 have? 2. Even calcium way down here? Yeah. Even calcium way down here has 2 valence electrons. So 1 valence electron is 2 valence electrons. How many does boron's group have? Boron's group at group 13 has how many? 3. Carbon's group has? Nitrogen's group has? Oxygens, the halogens, and the noble gases? 8. Okay, so group 1 has 1, group 2 has 2, group 13 has 3, group 14 has 4, group 15 has 5, 6, 7, and 8. How many valence electrons do atoms want to have? What is our ultimate goal? 8. Okay, 8. So watch this. Fluorine has 7 valence electrons. To complete its octet, it gains 1 more. What is the charge of an electron? -1. If it gains 1 more electron, then the charge it has when it has completed its octet is -1. Its oxidation is -1. I'll go over it again. The halogens, fluorine, chlorine, bromine, iodine, have 7 valence electrons. To complete their octet, they need to gain 1 more. That 1 more they gain has a -1 charge. So, 0 plus a -1 is -1. The oxidation state of all of fluorine's group is -1. How many electrons does oxygen's group need? 2. What do you think their oxidation state is? -2. Nitrogen's? -3. Carbon's? Yeah, carbon's interesting. Carbon's group has 4 valence electrons. It is equally easy to gain 4 more as it is to lose 4. So carbon's group is +4 or -4. I'll explain that again in a second. Lithium. Lithium's group has how many valence electrons? 1. If it loses that valence electron, what's the resulting charge? +1. So the oxidation charge, or the oxidation number of all of group 1 is +1. See how this works? +1, +2, +3, plus or -4, -3, -2, -1. Halogens are what? Or the noble gases are what? 0. They already have their octet completed. They don't need any more. 0. So that's oxidation. It is the charge an ion has when it has completed its octet. +1, +2, +3, plus or -4, -3, -2, -1, 0. Mr. Byers, are there exceptions to the rule? Oh yeah, you better believe it. If you take chemistry AP next year, you're going to have to deal with all the exceptions. This class, no exceptions. Give me a thumbs up if you're with me so far. A question first.
I have a question.
Mhm.
It may sound kind of stupid, but
I'm sorry.
okay. Well, I know you see there's a pattern for the valence electrons, but like, how do you tell their like how do you know that potassium has 1 valence electron?
How do I know the potassium has 1 valence electron?
Yeah, I mean.
Potassium's last electron is in the 4s1 orbital. So level 4, 1, 2, 3, 4, s block 1 over. So the last electron is 4s1. So far so good? Okay. The valence electrons are the total number of electrons in the highest s and p orbital. So the highest s and p orbital for level 4 is 4s and 4p. Potassium has only one electron in that 4s and 4p, so it has one valence electron. On the other hand, on the other end of the periodic table, krypton has filled up its 4s and its 4p, 2 for the 4s, 6 for the 4p. Krypton has 8 valence electrons. Am I being clear? Okay, give me a thumbs up if you want to move on. All right, let's move on. Okay, so these are the elements. Don't write this down. I'm going to give you, we're going to go over each group one at a time. So these are the groups we're going to look at. We're going to look at the alkali metals. We're going to look at the alkaline earth metals. We're going to look at the transition metals. We're going to look at the main block elements, old main block. We're going to look at a special group of the main block called the halogens. We're going to look at the noble gases, and we're going to look at the rare earth elements. Okay. We're going to look at some properties of the groups specifically, starting with alkali metals. All the alkali metals end S1. They all end something S1. So lithium down through cesium. And one that we didn't mention, we don't have on board, called francium. Francium is, yeah, super artificial. Okay. So group 1 elements, they have one valence electron. So they have an oxidation of +1. They're soft, highly reactive metals. Most people, when you think about sodium, you think of like table salt. That's not sodium. That is a compound of sodium, but not sodium. So, when we use sodium later on, like pure sodium metal, you'll notice it's a metallic cube. So it's a metallic cube, and I'm going to cut it with a knife. It's soft like clay. You just cut it with a knife, but it's metal. So they're soft, highly reactive metals. They're lustrous. Lustrous is a fancy, sciencey way of saying what? Shiny. Yeah. Lustrous is just a fancy way of saying shiny. They're electrically conductive. They make really good ions. Part of the reason that we use lithium in batteries is because it makes such really great electrolytes. We've been using group 1 metals in batteries for decades before there were lithium-ion batteries. Alkaline batteries are called alkaline batteries because they use an alkaline metal electrolyte. Alkaline batteries are like 1.5 volt, AA's, AAA's. Those are alkaline batteries, D's. They're called alkaline batteries because they use an alkaline metal electrolyte. I hope we get to electrochemistry in the spring, because electrochemistry is pretty fun. Learn about how metals swap electrons. Okay. Next. Crazy thing about alkali metals, they're metals, but they have low melting points. It doesn't take much energy to melt them from a solid down to a liquid. In fact, liquefied sodium is used in industry, even though it's really, really dangerous. Used properly, it can be very handy. They have very low densities. Yes?
What makes something a metal?
purposes of this course, things on the left side of the periodic table, if they have, that's a really good question scientifically. For purposes of this course, anything that's the D or the S block, besides hydrogen. So S block or D block, these are the metals. As far as what makes something a metal, having the properties of a metal, basically.
Well, I was just wondering because you said you can cut the sodium. Weird.
Mm-hmm. Yeah, it's a metal, but it doesn't hold its atoms as closely together as like gold or silver or platinum. So yeah, you can. If I gave you a piece of sodium, you could just bend it and rip it apart. You could be like, it would hurt while you did it because sodium drops the water in your hands. But if you had like gloves, you could just go rip, rip. It's like clay. Okay. Oh, were we done with group 1? So group 2 are called the alkaline earth metals, and they behave just like the alkaline metals, but less so. They all end S2. They have 2 valence electrons, and they have a +2 oxidation. So the alkaline earth metals, they have 2 valence electrons. That gives them a +2 oxidation, and their ending configuration is S2. And their properties. They have the same properties as alkaline metals, but less so. They are less lustrous. They are less electrically conductive. They are more dense. But for the most part, they behave pretty similarly. They have slightly higher melting points. So they're like wannabe group 1s. They behave just like group 1s, but less so.
Mr. Byers,
Mm-hmm.
when you see sodium on our bags of chips,
Mm-hmm.
is that a compound? Like, so if it weren't, it'd be dangerous?
Yes. The sodium that's written on your bag of chips are sodium ions, not metallic sodium. Metallic sodium are sodium in its purest form. The sodium that they rate on your chips and that you need for your brain and your muscles are sodium ions. So next time someone says you're going to have a no sodium diet, you're like, okay, well, you can eat it if you want. But if you're like, I'm going to have a no sodium diet, I'm like, great, I'll pick out your casket. Because you need sodium for muscles and brains. Every time a neuron fires, an ion of sodium gets used up. Every time a muscle cell contracts, an ion of sodium gets used up. You know why people get cramps?
Sodium?
Not enough sodium. You know, people get headaches? Too much sodium.
People talk
Yeah.
a lot.
Yeah, people talk. You give me a headache, Mr. Byers. But yeah, sodium's important. But if you get too much of it in your blood will swell up and you'll get a headache and you get high blood pressure and your heart has to work. Your heart has to work harder.
Isn't that what Mr. Hardy had?
Yep. He still eats cup of noodle for lunch.
Can't stop the man.
The heart wants what the heart wants, I guess.
I mean, it's better if you just don't drink the juice, I guess. That's where all the sodium is.
Juice is not too bad. Whole juice is better, but whole juice is also really expensive.
No, I meant like in the cup of noodles. Like if you put
Broth.
the water. The broth.
The broth.
The broth.
The broth. That's a good point. Yeah, don't drink the broth. Just have the noodles.
But that's the best part too, actually.
Okay. So, any questions about group 2? All right. Group 3 through 12 are the transition metals. What we've been calling the D block. They're going to end something D something. So group 3 through 12 are the D block, the transition metals, and these are called multivalent because they can have multiple valence charges, so they can have multiple oxidations. Their oxidations can be between +1 and +7. That's very confusing, Mr. Byers. I know. The good news is we don't have to deal with them until you get to take, if you want to take physics or chemistry AP, then you'll have to deal with them being multivalent. But in this class, we don't have to worry about them being multivalent. You used to have to remember what, memorize what the charges were. Now you pretty much just know they are multivalent. And we used to have to make people do that. But so group 3 through 12, the D block, they can be anything from +1 to +7, but they will always have an oxidation that is positive. Okay? So some properties. What are some properties of the metals that we usually think of as metals? Iron, copper, cobalt, whatever. What are some properties?
Shiny.
They're shiny. Yeah. What else?
Iron dust.
They have that taste.
They have that taste.
You know that metal taste? I don't know.
Yeah.
It's
Take
weird.
the metal
I don't
taste.
do that weird, but they do.
That has to do with their free-flowing electrons. Yeah. They're hard. Exactly. That has to do with free-floating electrons, which we'll talk about next unit. Yeah. They're hard. What else?
They're not electrically conductive.
Are they? They are. Copper wire. Yeah, the copper wire that makes up a little speaker in your cell phone. Yeah. So yeah, they're lustrous. Very. This is where we have metals like silver, what we make mirrors out of. They're electrically conductive, thank goodness, because we can make wires and electronics. And here's a fun word. They are malleable. Things that are malleable can be bent to your will, and they will hold that shape. So you're like, I got a little brother, he's cool, he's malleable, I can make him do my chores. For a chemical, you can bend it, you can hammer it into thin sheets, you can form it into something, and it'll stay that way. Makes metals really good at making car parts and paper clips. And knives, and sinks, and table legs, and braces, and glasses. And rods.
Clay. No clay.
Let's list all the things we can think of that are made out of metal. Also, they are ductile. Ductility is an ability to be drawn into very thin wires without breaking. Metals are ductile, and thank goodness, because thin copper wires are really handy for making speakers and telephone wire, without which we could have the internet. Wire all over this place. And of course, they are very hard, very dense, and have very high melting points.
Can we do that thing they did on Mythbusters where they had molten lead? They put water on it and dip it in with
If you can find enough molten lead,
little fuck.
yeah, sure. Knock yourself out.
It was cool. Did you see it?
Oh yeah.
That was cool. I used to they put some market. I'll probably sell it down after
Do you know why? Do you know why they were able to do
I
that?
think the water made like a shield around their fingers and evaporated while they're still in.
Yep. Got the little gas chamber.
Yeah.
Yep. Shoot, I used to know what that effect was called. Oh well. All right, so this is where we have the element iridium, one of the hardest elements on the planet. where we have osmium, the densest element on the planet, and where we have tungsten, the highest melting point that we can use. Okay, so after the transition metals, we have what are called the main group, or the main block elements, group 13 through 18. This is where we have elements with the widest variety of properties. We've got some zany stuff in here. This is where the action happens. This is where the crazy stuff is. So, once again, since the main block has between 3 and 8 valence electrons, we have properties, we have oxidations from +3, +4, -4, -3, -2, -1, and 0. And again, there are exceptions. We're not going to deal with the exceptions. But you're welcome to come back a year from now and say, Mr. Byers, I learned that there are exceptions to the rules you taught us. Well, yep. But you didn't need them last year. Okay. Main group. Liquids, solids, and gases, all in the same block next to each other. You got selenium, solid, right next to bromine, a liquid. You got sulfur, a solid, right next to chlorine, a gas. You got carbon, a solid, right next to nitrogen, a gas. You got bromine, which is a liquid at room temperature, between chlorine, which is a gas at room temperature, and iodine, which is solid at room temperature. And one of my favorites, you have a healing chemical right between two poisons. Anyone ever take that pink sludge that makes you feel better when you have a bad tummy? Yeah. Doesn't work for me. Not today, anyway. Yeah, Pepto-Bismol. So, Pepto-Bismol is actually bismuth subsalicylate. Has bismuth in it. Bismuth is hanging out right here between lead and polonium. Lead will kill you. Polonium will kill you even faster. Bismuth will heal you. Very strange. Yeah. And this is where we have arsenic, which will also kill you, right under phosphorus, which is in every living thing. Isn't that weird? Yeah. That's where you have the main block. Lots of crazy stuff going on in the main block. This is where we find the metalloids. Metalloids, also called semimetals, not to be confused with precious metals. Semimetals or metalloids are elements that have properties of both metals and nonmetals. Silicon, germanium, antimony, arsenic, these are our metalloids. Gesundheit, Gesundheit. When most people think about silicon, you usually think about like gooey stuff, like silicone spray or silicone gel, or silicone breast implants. But silicon is actually a metalloid. It has, I showed you silicon at the very, very beginning of the year, a vial of it. It's like, it looks like glass, but it sounds like metal. Yeah. It's shiny, but it's also crystalline. So this is also where we find the halogens. So let's talk about the halogens. Group 17 are the halogens. So group 17 are the halogens. They have how many valence electrons? 7. How many valence electrons? How many valence electrons do they want? 8. 8. What are they going to do? Yeah. Questions? Or you just joined? Okay. So yeah, they've got 7. They want 8. They're going to try really hard to get 1. Halogen means salt former. This is kind of cool. So they're very reactive because they have 7 of 8 valence electrons. They're so close. But yet so far. because they have almost completed their octet, they have a very high electron affinity, very high ionization energies, and they can attack and bond almost anything. Fluorine can attack glass. Scary. So 4 of the 7 diatomic molecules, remember Brinkelhoff, 4 of the 7 diatomic molecules are halogens. We don't really care about astatine. So in other words, they're all diatomic. Okay. 2 more groups left. What's the next group we're going to talk about? Yeah. I really don't have to tell you anything about the noble gases you don't already know. It's the NP6. They're mostly unreactive. They have filled octets. They have near zero electron affinity because they have filled octets. They have very high ionization energy. Same reason. And you get them from the ocean. Yeah, like, where do you get the noble gases? Well, you can't go dig it up out of a mountain because it would just evaporate into the air. You get them in the ocean. One thing that's also really neat about noble gases is they form high energy plasmas when you run electricity through them. Want to see one? Of course you do.
This is actually the Akeda training center.
ISIS 101, right?
You ready for the plasma? Plasma! That's not like cool, right? This is. Maybe you think it's cool. When it works. Oh yeah, that works. That works too.
Wait, what did he do with my finger? I'm after curious.
Oh, it won't stretch.
Woo! That woke me up. John would love that stuff. You got expelled for, he got
Wait, why does
suspended.
that go against?
Ooh.
I can't say for sure, but most likely it's interfering with the signal. It's creating electromagnetic interference. So it's interfering, it's sending out radio signals interfering with the signal coming from the computer. That's my guess. Okay, so last group. What's the last group we need to talk about?
The rare earth element.
Yeah.
Rare earth elements. All right. So the rare earth elements are a lot like the D block metals, the transition metals, except one huge difference. They're big, which frequently makes them what? Radioactive. Most of them are radioactive. and found in China.
Does that mean they're unstable?
Yes,
Is that what radioactive means?
that's what radioactive means.
Okay. Just want to know.
Yes.
I was like reading on just looking at my calculator list. I read this thing and it said there was a G block.
There might be.
What does that mean?
It would, a G block orbital would have 1, 3, 5, 7. It would have 9 or like orbitals for 18 electrons. They're thinking, you know, super theoretically. We don't have the technology to look at that deeply. But who knows? Maybe there is. It's entirely possible that the periodic table that your kids learn about will look differently than the periodic table that you're learning about now. Because as our technology gets better, our understanding gets better. You know,
So our kids are gonna be smarter than us?
unlikely.
Unlikely.
So, but yeah, it's all theoretical. It's again, when you start thinking about science fiction, you could be like, we don't know, because let's just make something up. So that's where we are.
They get virtual reality.
Okay, so the lanthanides are the top row. They are the lighter rare earths. They're the 4Fs. And then the actinides are the 5Fs. Again, this is pretty much the only exposure you need to have to the F block in this class. We just don't, they're not useful to us at this level of chemistry. I miss my sky.
What happened to it?
They covered it up.
They-
Uncover it. No, they worked really hard to cover them up. My room is special. The other rooms that it was interfering was creating glare. But my room has a smaller skylight, so it doesn't have any glare. But now it has no glare at all. No skylight. Okay, the word we use, this is where we're finishing today. The word we use for elements that are heavier than uranium is trans-uranium, which literally means beyond uranium.